Now it's better. I heard myself that something is wrong. Just because organizers told me that I should speak on to people who are working or studying physics of elementary particles, high energy physics, I had a lot of memories, because when I was 20 years old, I won the competition. There was an enormous competition to study the theory of elementary particles. And I moved to a huge institute of elementary and theoretical and experimental physics in Moscow, which at that time had, just in the center of Moscow, had a lot of nuclear reactors, accelerator, and so on and so on. And we had dormitory on the half of way from nuclear reactor to accelerator. You know, I still surviving. Yes, it was alive. But when I was on the 5th year of education, after 1.5 years in elementary particle physics, I met one person, Zeldovich. In reality, I didn't know who is him, but people told me that he is organizing a group in theoretical physics, and it's very difficult to be accepted by him. I decided just to try. Is it possible will he accept or not? I came to him, and after long conversation, he asked me what I am interested in. I am really interested in theory of fields. I told, oh, it's giant science, but I like also experimental lectures, because they show how it is possible to prove theory, that you are just can make experiment which proves theory, and you can also predict some test theoretically, and then people can prove that this science which you are proposing is correct. And I don't know why, but he liked this, and he invited me to come to his group. And then he told me, oh, we will do astrophysics. But head of my chair of elementary particles, he told me, no, Rashid, don't go to Zeldovich, because you will do astrophysics, and it's absolutely useless science. But Zeldovich gave me 3 problems. I solved them in a week time scale, and he told me, I will take you. I will be your advisor for your diploma. I told him, no, I don't like to do astrophysics, because our chair told me that astrophysics is useless science. He told me, okay, help me with 5 small problems. It was for 3 problems, it took only 1 week for you. And then we will work in theory of fields. I told, okay. After months, I solved that problems, and I told I never returned to elementary particle physics, because problems which he was giving were unbelievably interesting. And I was enormously lucky, because in several months, he agreed to be my advisor in March 1965. And in the June 1965, Penzias and Wilson, Nobelists now, they discovered cosmic microwave background radiation, which was theoretically predicted by George Gamow. And why it is so important? You see this radiation, whole sky, and when people measured it, they found the temperature of this radiation is 2.7 Kelvin. And there are no deviation on the level of 10 in power minus 5 from black body spectrum. This was absolutely the best black body among all known objects in the universe where we are measuring spectra. just absolutely the best, 100 times better. Because normal stars, they have black body with 10% deviations, and here 10 power minus 5. It was unbelievable. In second, they told measurements, first measurements, spacecraft of Kobe, it showed that this radiation is unbelievably isotropic. There is only one anisotropy which was found, is connected with our motion. Earth is moving around Sun, Sun is moving around center of the galaxy, and our galaxy is moving towards Andromeda. And we discovered some of these velocities due to just Doppler effect on this CMB. And this was unbelievable discovery. They came immediately, and I was very lucky. But I can tell you that today, after 65, how many years? It's 57 years gone. I was student, now I'm already not very young. As you see, I can tell you that a lot is discovered. And we, just with my advisor, predicted the anomalies in the spectrum of cosmic microwave background, which are only 3-5 times smaller already now than upper limit from the Kobe spacecraft, which made this the best black body in the world. No, it is not real black body, there are deviations. And I will tell you about deviations, and physics, just simple physics, immediately gives you that universe had two great milestones in the evolution of the universe. I think that many of you read these beautiful popular books like First 3 Minutes of Weinberg and so on, that there were, George Gamow wrote about everything. There was time when we had positrons and electrons in equilibrium. You know, temperature in the past was higher than today. There is redshift, and if I multiply this temperature 2.7 Kelvin to, for example, redshift 10 to the power 8, temperature will be 3 times 10 to the power 8 Kelvin, and it's very close already to produce electron-positron pairs, just in equilibrium. And then equilibrium was that and our universe has a normal entropy. Per every baryon or every electron in the universe, we have 10 to the power 8 photons. It's unbelievable how much. Only these photons, excuse me, which are in the cosmic microwave background. Let us look to the first slide. In addition, it was in the same time when I came to Zeldovich, people became enormously interested in clusters of galaxies. Clusters of galaxies are the most massive, gravitationally bound objects in the universe. And these objects are unbelievable in their properties. Look here. There are thousands of galaxies within this cluster of galaxies. Able 2218, and these galaxies, each of them has velocity of the order of 1,000 kilometers per second. They are moving in gravitational potential of the cluster of galaxies with huge velocities. And Fritz Zwicky in 1930s, he told that something is wrong with clusters of galaxies. If I will take kinetic energy of all galaxies, it will give me mass of the cluster of galaxies, 10 in power 15 solar masses inside one cluster of galaxies. But if I will measure off all 1,000 galaxies there, mass will be 100 times smaller. And he told first time that there should be dark matter. It was in 1930, and only in the 1980s, Vera Rubin, Yana Nast, and other people, they told, yes, this is true, there should be dark matter. And today we know maybe 10 different experiments which show that there is really dark matter. But first were these clusters of galaxies. And they are very interesting because distant galaxies, you see here gravitational lenses, you see them. Many in one cluster of galaxy. This is dark matter is focusing radiation, radiation from cluster of galaxies, from galaxies which are very far behind cluster of galaxies. And they are, by gravitational lensing, they are becoming very bright, and we see and we can study them near us. And I can tell you again, I can repeat that what these most massive gravitationally bound objects in the universe, what they consist, what are their constituents, components. These are few percent, excuse me, what is, few percent of the mass is the total mass in hundreds of galaxies and in stars which are in these galaxies. This few percent of the mass. 15% of the mass, it is hot gas with sound velocity equal to average velocity of the galaxies, 2,000 kilometers per second. And 80% of mass is dark matter. And we now are observing 10,000 of clusters of galaxies. All of them have dark matter, and all of them have of the order of 80% of mass is the dark matter. It's just experiment. Let's go further. And when I came to Zeldovich told me, try to think, is it possible using CMB to detect clusters of galaxies on the sky? Gas is hot, maybe there is something. And I spent maybe half a year thinking what should be there which it can do this. I will not tell you. For example, if you think that in isotropic radiation, cluster will scatter radiation, and I will see the decrease of brightness. Absolutely wrong. In isotropic field of radiation, effect is zero. Cluster is invisible, just scattering, Thomson scattering. But it was very interesting because when I considered the line, you see here, laser line, and this laser line is scattered on isotropic electrons with temperature 100 of keV, of mass of electron. You see 5.1, in reality 5.11 keV temperature. People were asking me why I'm using this ugly temperature, 5.1, because KTE divided to 5.11 keV divided to mass of electron is exactly 100, and on my ruler, it was much easier to compute. No computers at that time, nothing. It was just logarithmic ruler. And you see what is occurring. If I compute this line, there is a Doppler broadening of the line due to the scattering of the electron, Thomson scattering of photon on the hot electrons with velocity v, but velocity, average velocity, excuse me, is equal to 1/7 of velocity of light. Therefore, I computed also second order correction on VC. And you see that the right wing of the line is brighter significantly than the left wing. And then everything was easy. I came to Zeldovich and told, look, if I have blackbody radiation, Planckian radiation, excuse me, and there are many laser lines, and every laser line shifts to what higher frequency as here, then I will get this spectrum. And most interesting here was the following. This is blackbody, and this is scattered photons. And there is decrease of brightness in the Rayleigh jeans of Planckian curve. And this was unbelievable. You immediately getting effect. You have shadow on the sky if you have cloud of hot electrons. This was predictions, and many people, I can tell you, 100 experimental groups of radio astronomers were trying to detect this for 30 years. It was impossible. Then came John Karlstrom and his group on the South Pole telescope, I will show it. They started to discover unknown before clusters of galaxies and telling this is cluster, this is cluster, this is cluster. First three immediately were confirmed by optical observation and X-ray observations, and people found that it's possible just using CMB to find these clusters of galaxies. I am showing you here, this is just shadow. You know, you are scanning the sky and then you have just hole on the sky or negative source on the sky. This was, I can tell you, once I was giving talk in the Physical Institute in Moscow, and very old person, absolutely gray, told me, you are wrong, young person, because I am teaching thermodynamics and statistical physics for 30 years. You don't know Kirchhoff's law, and therefore you are wrong. If gas is hot, it should emit and cannot be whole. I was trying to explain him, this is scattering, not real radiation. It is, no, Kirchhoff's law is not working. And then Zeldovich came from his dentist, and he just entered and told, oh, Rashid is correct. And everybody started to say, yes, yes, yes. Then I remembered Napoleon. It is great when heavy artillery is behind you. You know, it's absolutely great when you have great advisor. Yes, I showed you this. Let us jump ahead. Great Planck spacecraft, this really great cosmological spacecraft which observed the sky and looked for cosmological fluctuations, perturbations. Great because it immediately discovered during its scan of the sky 1,500 new clusters of galaxies which were unknown, and they were unbelievably massive. These were clusters of galaxies with mass again higher than 10 in power 15 solar masses. I told you that these clusters of galaxies are most massive gravitationally bound objects in the universe. Theory predicts that within observable universe, in the universe with a radius 13 billion years, there are only 100,000 clusters of galaxies. And today, practically 20,000 clusters are discovered using this method. You know, when you are coming to great advisor and when you are working very hard, I was working every day till 4 in the night, trying to do something good, then results are coming. You see here the nearby cluster of galaxies, comma. You see it here, where Zwicky discovered the dark matter, and this is the image of comma in the Planck data. You see it, how the distribution of gas, and there is another small group of galaxies which went, now we know this, through the center of comma, and there are many shocks, contact discontinuities and so on. You see beautiful hydrodynamics, with characteristic time 1 billion years, you know, just on the sky. And this is coming from just well-known data of Planck spacecraft. Now I show you the giant radio interferometer on millimeter wavelengths on 5 kilometer altitude in Atacama, Chile. You see it here, a lot of dishes. And this is the image. Blue is the image of the sky obtained by these 64 most sensitive dishes in the world. On height, because atmosphere is okay there, and it is good to observe. And you see this black part here, this black part here, this is shadow which we were able to predict at that time. You remember. And this is, and I can tell you that resolution is enormously high. Again, you see here the shocks, outflows from galaxies, a lot of different things, and this beautiful science. But most important, there is a hole caused by, you know, a Z effect. This is Z, it's Zeldovich. It's here seen in the ALMA observations. And all overlay the picture above with bright objects. This is Hubble Space Telescope image of this region in optical. And you see the galaxies and normal baryonic matter, which I told you only few percent of the mass. We see 15% is a hot gas. And I told you already about South Pole Telescope. Just very close, maybe there are people from this neutrino installation there, cubic kilometer, and this is a telescope, 10-meter telescope, which discovered only 6,000 clusters of galaxies using this effect. This is the Atacama Cosmology Telescope, also in Atacama Desert, 5-kilometer height. You see this dish. I am not, they also discovered more than 6 or 7 clusters of galaxies. I told you the goal is 100,000. All clusters of galaxies in the visible universe. We can see them because effect doesn't depend on the redshift. If there is cloud with hot gas, we will see it at any distance. It's beautiful, but formulae are very simple. Spectrum is the same of the whole at any distance. You can do this. For me, it's important when this Atacama Cosmology Telescope started observations, they had detectors, focal plane detectors had 30 cryogenic bolometers in the center. Now a new version. Lyman Page just told me about this on the conference connected with 550th anniversary of Copernicus, Nicolaus Copernicus, and he told me that now they are installing 40,000 cryogenic bolometers in the focal plane. And hundreds of people are staying, producing these bolometers, Argonne National Lab is producing, and there are many, many things. A lot of people are working. And it's very interesting to see what is coming from simple theoretical idea. I will tell you about next steps. I can speak about just individual objects a lot, but it will be interesting maybe for you that universe is unique thing. It has very high entropy, I told you. And what is interesting in our universe, that, you know, I do not see laser, it's interesting. Yes, but upper part, adiabatic expansion of the universe preserves blackbody spectrum established in early times, for example, during electron-positron annihilation. And there are invariants. We know that temperature is just increasing with redshift 2.7 multiplied to redshift. And this is the temperature of matter and radiation. And this is very good. And I told you already that John Mather got Nobel Prize because he discovered most perfect blackbody. And this was 38 years ago. Now, there is great progress in the technology of experiments and especially of detectors and cryogenics. And PIXI proposal from Goddard Space Flight Center is promising that it will be 100 or even 1,000 times more sensitive than Kobe-Fires instrument. It's so important. We predicted with Zeldovich that there are 2 main type of spectral distortions, Y and mu. I will tell a few words if I will not finish on time, will be able to finish my talk on time. I can tell you that what is important. For example, if in early universe some unknown particles are decaying and some theoretician is telling there should be energy release, then there will be spectral distortion of CMB. And because they are absent, there is upper limit to amount of these particles, to their lifetime, and so on. A lot of things is possible to get. The same is with dissipation of gravitational waves, primordial black holes. People got a lot of information what unusual might be in the before when I was young. It was possible to say, oh, I have such theory, nobody will ever observe, but there were primordial black holes. Now we can say, yes, maybe there are primordial black holes, but their mass should be smaller than this, their spectra should be different, and so on, and their lifetime should be longer. In opposite case, they will contradict to these observations. Okay, and I can tell you, excuse me, also, today I will speak only about unavoidable spectral features, which are predicted within the standard cosmological model. Just everybody believes there is this model, and from this model you immediately find that even it is producing some spectral distortions. Look, what is I will speak today about 2 milestones. First milestones occurs when universe was 380,000 years old. In this moment, temperature of radiation dropped from very high in the beginning of the expansion of the universe to 3,000 Kelvin. And according to all formulae and theories, there should be recombination of hydrogen. Hydrogen should be neutral, and before all hydrogen is ionized. Thomson scattering optical depth, probability to scatter in the universe is hundreds or thousands or millions. Therefore, it is impossible for photon to come to us. Then, in very short time, universe recombined. No free electrons. If no free electrons, photon can come and just reach us. And we can say how non-uniform was universe when temperature of radiation was 3000, and this was when universe was 380,000 years old. It's reality, you can prove this. This thing is the surface of last scattering, and it is unbelievable because Planck spacecraft now has 3 papers about the cosmological constants in the universe. And these 3 papers, release 1, release 2, release 3, have now more than 30,000 citations. First paper now has 8,000 citations, second has 10, and last one has now 11,000 citations. And they are coming every day, these citations, because all physicists use it, all theoreticians. Second thing which is very important, I told you that there are spectral distortions. How long we can see these spectral distortions? When physical processes will make you blackbody radiation which we are observing. And answer, again, we with Zeldovich solved it in 1970, and there is blackbody photosphere, and redshift is 2 times 10 to the power 6, and temperature at this time was 6 times 10 to the power 6 times 10 to the power 6 Kelvin. You know, with temperature maybe 10 times hotter than solar corona. And this was blackbody photosphere. And this occurred when the universe was 18 years old. Very young, good age, 18 years, you know. But at that time was blackbody photosphere. If energy releases before this point, then everything, all spectral distortions will disappear. We will see just blackbody. And you remember that there is a beautiful book of Steven Weinberg, First 3 Minutes of the Universe, that during these 3 minutes, therefore, nuclear synthesis was there, all our helium was created at that time, deuterium was created at that time, which we observed helium-3, and so on and so on. And there was also electron-positron annihilation, for example. Therefore, I will speak about one event that when universe was 18 years old, and second, when universe was 380,000 years old. I remember also, for me, this was shock in reality. In the spring of 1966, Zeldovich came from some meeting on the nuclear physics, which was, you know, semi-secret and so on. And then he told me that he has no time to read new paper, which came from giant theoretical astrophysicists at that time, Laser from Harvard University, Professor Laser, and Jeff Burbidge. Then he became a rather good friend from Caltech, because they stated in '66 that CMB spectrum is just the stellar light thermalized by the dust. And Zeldovich told me, tell me how it is possible. Are they wrong or not? I told in 1 day that they are completely wrong. Reason was that it's impossible to make uniform distribution of temperature, but I was interested, is it possible to do, can I consider that physical processes in the universe are the same as in the stars? What will be the optical depth for Bremsstrahlung, for free emission? And free emission, Rosalind mean, was negligibly small. Up to redshift 10 to the power 8, it was only 10 to the power minus 5. No absorption, free absorption, no free bound absorption, nothing. Universe was absolutely transparent for continuum radiation. I was shocked with this because I never thought that such objects are possible. And second, what I was amused, I computed what is the Thomson optical depth. And Thomson optical depth was huge, 2 times 10 to the power 7 up to redshift 10 to the power 8. Just free electrons were not permitted to photons to travel to us.